up next, we have Matthieu. Looks like screen is up. So with that, please, Matthieu, take it away. Oh, you are muted. So sorry. Matthieu, you're muted. So sorry.
Do you hear me?
Yeah.
Okay. So yes, I was saying that the main motivation of this work is that there is an urgent need of green computing. Currently, more than 10% of world electric production is used by IT systems. And if we look into details, it divides in 3 parts: networking, storage, and computing, and it's almost equivalent parts. So if we want to design frugal systems, the savings must address all these aspects: storage, computing, and networking. So I'm going to focus on the special case of scientific data because it's a large part of the global IT consumption. What we call scientific data in general are arrays of correlated numbers in IEEE 754 formats, floating point formats. And in general, they encode rather smooth surfaces which correspond to results of simulation or to observations. Just to give some orders of magnitude, by 2035, it is planned that the ITER reactor, which is a nuclear fusion reactor, will produce 2 petabytes of data every day. And if we watch at the data used for climate simulations, when we can wonder if we're not just going to warm the planet just by doing these simulations. Okay, so some state of the art. I'm going to go very quickly on that, but in general, there exists lossless and lossy compression techniques. And also another criterion is that there are fixed rate and variable rate compression techniques. And in general, a compressor is not only one algorithm, it's a pipeline of algorithms. For example, this is the pipeline for the JPEG formats. Okay, you use a sequence of algorithms, not only one. So concerning scientific data, there are 2 main approaches to build compressors currently. The first family is like ZDFP, at least in its first version. So the user sets a compression rate, and you will obtain an error which is a function of this compression rate. If you compress a lot, you will have a large error. If you compress less, you will have a smaller error. And you can adopt the converse approach, which is what does the SZ compressor. You set some error threshold, and you will obtain a compression rate. If you want to have a small error, you will compress not so much. If you want to have a larger, if you accept to have a larger error, you will have more compression. And this is just a famous picture from a ZDFP paper. This is an original image. This is what you obtain if you compress and uncompress it using only 4 bits per double precision number. And this is what you obtain if you only use one bit per double precision number. Okay, so if I come back to my initial objectives, these tools like ZDFP and SZ are good to save storage and by way of consequence to save networking, because if you communicate compressed data, then you use less bandwidth. But they increase computing because when you want to compute. You have to uncompress the data to make your computation and to recompress the results. So they do not allow to make savings on the three aspects that I consider at the same time. So the idea is to develop a new compressor which also enables to compute directly on the compressed data. This is what tries to do the BLAS compressor. So it's a lossy fixed rate compressor. It reduces the size of the data by 11 dot blah blah. It's block-based. That means that it works on blocks of size 8 times 8. And basically, the main advantage of BLAS is that it allows to perform basic linear algebra among the compressed matrices. So we're going to see that this saves computing. I cannot go, I don't have enough time to go into details, but BLAS, like the other compressors, has its own pipeline of compression algorithms. And in the current version, it is able to perform matrix addition, subtraction, and multiplication by constant on without any uncompression. And it can perform dot product and matrix multiplication on partially uncompressed matrices. Okay, so BLAS is available on GitHub on this page. It's freely distributed. It's written in C, and it has a rather clear API. You have normal matrices and compressed matrices. You have operation to get and set elements of a matrix, to write and read matrices in files. And then you have the element of operation, addition, subtraction, multiplication by constant, dot product, and multiplication. Well, the code is can be used rather easily, I think. Okay, so what we obtain with BLAS quickly. I don't have time to show much experiments, but a few ones. This is for the addition on the left, and for the matrix multiplication on the right. It's about time. So we have matrix sizes on the x-axis and time on the y-axis. The first curve is the red curve, is the time to add or to multiply by a constant uncompressed matrix. So this is there is no compression at all. It's the red curve. If you use ZDFP, it is slower because the values have to be uncompressed before the operation. And with BLAS, we're faster than ZDFP, but in addition, we are faster than with any compression, because since BLAS operates on the compressed data structure, there is less operation to perform to add matrices or to multiply them. Okay, so there is a very important improvement in terms of time. Obviously, we're going to have some losses in terms of accuracy. So for accuracy, you have the time measurements are independent of the values, but for the accuracy, I have to show some curves. So I take matrices which are discretizations of these functions. And this is also a comparison with ZDFP. Clearly, BLAS is less accurate than ZDFP. This is just if you compress and then uncompress my 6 matrices corresponding to these 6 curves. This is the mean relative error with BLAS, and this is what we obtain with ZDFP. So it's worse, but anyway, it remains rather small and I guess acceptable in many application cases. And this is for the addition of 2 matrices. So I take my 6 matrices, M1, 2, and 6. This is M1 plus M2 with BLAS, M1 plus M3 with BLAS, and on the bottom left triangle, it's with ZDFP. So this is M1 plus M2 with ZDFP, etc. So we have to compare this number to this one to this one, and so on. So we can observe that BLAS is not as good as ZDFP, but not so much in some rare cases. It wins, and in general, it compares even if it's not as good. Okay, I have also tried BLAS on more realistic data. So this is, I've almost finished. This is scientific data coming from a standard benchmark. It's this kind of curves for climate simulation. This is the original, the compressed one with BLAS. So by A, we cannot see much differences. And this is the overlap of the two curves. And if we repeat this with 20 other benchmarks, we can see that with BLAS, we have very small errors and rather acceptable errors. So that's it. Just to conclude, this is a first work in this direction. So I think it shows that it's possible to compute among compressed matrices, even if there are many things that should be improved. For now, it's not something very completely finished. It's also related to precision tuning, because when you tune a program, you also have arrays, and you want to reduce the accuracy used in the array. So this can be a way to do it efficiently. I would like to extend BLAS to other linear algebra operators, to use real-world application, to use various compression rates, to have parallel versions, and maybe to have a version for embedded systems. Thank you for your attention.
Super cool work. And Samir has jumped in immediately with a hand.
Yes, this is very cool. I have two questions, and we can discuss it at length on the Slack. The first is that because you're assuming that the data is sort of correlated as it is laid out in the matrix, in some sense, another way of thinking about what you're doing in terms of compression is that you're really doing sort of a approximation. You're doing it blockwise, and you are even though the analogy that you're using is JPEG compression, you're approximating the original sort of function surface here with a set of sort of basis functions, and then doing operations on those. So one thing that comes to my mind is maybe we can develop an actual theory here instead of thinking of it in terms of compression, but actually as an approximation theory, as in how can you perform matrix operations by approximating them using 2D data or 3D data as some sort of as an interpolation and an approximation problem. And then you could imagine that you can use different classes of basis functions or different kinds of matrices instead of just blocks. The other question, which is sort of related to this, is that you had a fixed rate sort of approximation scheme, but that seems odd to me, because for some matrix operations that would be okay, but in other matrix operations, depending on sort of the conditioning of the matrix for that operation, that may or may not be okay. So have you thought about how you think about compression rates and the operations that are being performed in the matrix? Because once you compress the matrix, you may have already lost information to even think about what will happen.
Yes, there is several ways to make the compression rate variable. For example, there is a quantization at some point, so we can quantize, put to zero more or less coefficients after the discrete cosine transform. Things like that can be done. One other point is about the correlation between the data. That's true, but this is the assumption made by the other compressors too. If you have random data, it's difficult, even for images with integer in JPEG or things like that. Everybody in compression when you want to have a compression algorithm, you use this kind of assumption. Yes.
Any other quick questions for Matthieu? I am really excited about this. The compressed data thing has been interesting for a while. I remember the first time I saw ZFP and was just sort of blown away. The idea of computing on it's really exciting. I imagine also there's going to be some hardware people who are really interested in how you optimize the rest of the stack for these formats. So I think with that, friends, we have wrapped up the first session. The Slack is open, so please feel free to continue discussion there. I'm going to go ahead and pause the recording right now.